Yo wá kí n tiẹ̀ kọ́kọ́ lọ ra tí mo fẹ́ jẹ látàárọ̀ náà. Ọ̀dọ̀ àwọn ìyá rẹ̀ lẹ́ni látàárọ̀. Wọ́n ṣì wà ń bẹ̀.
Good evening, everybody. You're welcome to the free chemistry revision. Please, could everyone please be patient? We are about to start. And if there's anyone that you need to be reminding to join, should please join immediately. We will start by 8 o'clock on dot. Thank you.
Okay, good evening, everyone.
Hello.
Okay, can anybody hear me? Can everybody hear me?
Good evening, sir.
Yes.
Okay, okay, so we'll be starting by 8:05, and once it's 8:05, we'll start the class properly. So I'm just trying to stall a bit for some persons to join the call. So, but whenever they join the call, once it's 8:05, we'll start. So please, I would like you to turn down your mic.
Okay.
Do us a favor, turn down your mic so everybody will be able to hear clearly. Thank you.
Please can you turn off your mic? If you are just joining, just turn off your mic. We can hear you. Thank Shafirat.
Yes, ma.
Please turn off your mic.
Okay.
Thank you. All right, that's perfect. Who is that? Okay, Olamide. Please, Olamide, can you hear me? I think he's on transit. And Oluwatunifemi, please turn off your mic.
Okay.
Thank you. Olamide, please turn off your mic. You are supposed to turn off your mic immediately after joining. Is it a regular? Please turn off your mic. Olamide, thank you. Please, if you are joining, just turn off your mic because it's to cause noise for everybody. Thank you very much. Like he said, we'll start very soon. Ol- Olamide, Olamide,
Why are you shouting? Because if you know can you first complain again. Two first, I told Daniel two first. Maybe has you heard a hole in your ceiling? Maybe I should rip the roof off the damn ceiling. Maybe you should stop
Olamide,
kneeling and not believing.
Olamide.
You're crying. You're shaking your boobs like.
Allow me, they turn off your mic now, bro. Let's start this thing.
Mr. IK, are you here?
Yeah, I am.
Please, can you
So,
mute Olamide or you remove him? Anyone? Thank
okay, I
you.
think you have permission. You have permission to do that. You could
Okay,
just
I have permission.
turn him off.
Let me check.
It's turned
Yes,
off now.
All right, let me check.
we can still hear you, Lamide. Just if you want to turn it off, Lamide, just you check down there beside your mic button. You see, you should see a mic button by your, let's say, your lower left, and you'd also see video call. So just toggle down or toggle off the mic button so you would know that you're truly turned off. Okay, so can everybody hear me now?
Yes, sir.
Okay, so let me start by seeing if I could share my screen. Give me a minute. Minutes. Okay, so as I was saying, can anybody now? Just feel free to turn on your mic also if you can see me. Hello, can
Not
anybody see my
yet.
screen? Okay, let me see.
Not yet.
Let me see.
No.
No, no, sir.
Okay, just hold on a bit, please. This.
Can't hear you, sir. Maybe network is disturbing.
Yeah. I've not. I think I've not started sharing my screen yet. I'm just trying to switch it on and turn on my light. So just be patient with me. Okay. See and V here. Okay. So you should see my screen a bit now. Let's see. GND. So good evening, everybody. You can see my screen now. I think yes. You can see my screen now, right? Oh, everybody sit on it.
No, sir.
Can anybody see my screen?
No, no,
Okay, I'm seeing one. You can see. What
no.
one thing now? I think you're supposed to be able to see my screen now.
Yeah, it's saying.
Yeah. I'm able to
Mm.
see.
Okay. Let me go to my Z slide. Okay. So is my screen clear now?
Yes, sir.
Can anybody see anything on my screen? Okay, if you can see something, so you can. Okay, just give a hand. So today we're going to be at chemistry, but what I would first do, someone's mic is turned on and it's kind of making noise. I don't know. So as I was saying, we'll be treating chemistry today, and I know many of the courses that we are having issues with chemistry. Most people selected chemistry, and I think that's why I started chemistry. What everybody sees it as very difficult. But this evening we'll be trying to see how we'll be having 2 classes on chemistry, but today is the first one. So the first one is going to be trying to see how we can break down the majority of the concepts in chemistry. We'll try to be fast because the goal is to see how we can touch the entire syllabus. Teaching it and you'll be able to ask questions. So stay around. So first off, many of us are feeling pressure. Normally in chemistry, we always see things like thermodynamics, stoichiometry, and many other big words, colligative properties, relative error. Some people get confused when they hear all these stuffs. And yeah, normally it's scary somehow. If you're someone that probably you're not really that interested in boring stuff, it would really feel boring to you. But it's not necessarily supposed to be boring. It's boring, but it could be less boring if I put it that way. So we'll be seeing how we would go through the entire syllabus on one mic on, and it's actually distracting. So we'll be looking at how we would go through this entire chemistry class and treat as many as we can treat into this lesson. So for me to be completely honest, for everything, if you look at can you hear me?
Yes.
Okay, so as I was saying, if we should be completely honest, if you look at chemistry textbooks, they are kind of confusing, as I said. When you start seeing thermodynamics, geometry, you be feeling like as if you should even get headache if you're trying to read it. Some people could just, once they start seeing all this, they just close their book. But it's not, you're actually completely normal if you actually have felt that way before. What I say is that chemists, people that wrote this textbook, they can be very terrible at naming stuff. They will be giving heavy words to simple something that they could just give simple explanation. They will take something that is very simple and they'll slap a complex name on it. So we've seen how some of these thoughts could be broken down, something less complex. So we'll be starting first off with basic SI units. I know this is something that everybody knows, but some people, I just feel some people might not really have gotten the full concept about it. So this is the portion of chemistry that I can say, to me, it seems like statistics, but both of them are still looking complex. So what is basic chemistry? I'll be trying to use a chef as my, what I call it, I'll try to use as a chef, I'll try to use a chef as, or a kitchen as my, would I say, case study. So I'll be using kitchen terms to try to explain what we'll be studying throughout today. So when we have something like a very big kitchen, a very huge kitchen, and we have to cook in that kind of big kitchen, there's always usually in a standard, always a lead chef. If you go to something like ShopRite or stuff like that, there's always a lead chef, and this lead chef, just imagine he's trying to instruct the junior chefs like, hey, I need you to cook so and so, and you should use just put Maggi, put pepper, put this. If there is no standard that the chef, every single new chef can be able to understand, if there is nothing that these chefs can be able to understand and measure, measure every time to get the measurement right. You think that this will share particular restaurant is going to be fresh, while tomorrow you can probably experience excess salt or even excess pepper. So that's exactly the same thing that basic SI units actually are. They are like a standard unit that everybody, every scientist can be able to look at and be able to say, okay, if I say 1 gram, a chemist in UK can be able to know what a chemist in the Germany can be able to know what I mean. A chemist anywhere all over the world can be able to understand what. So that's what the basic SI is actually about. It's actually trying to about standard unit that is universally acceptable. So they call it SI unit, standing for System International Unit. So you should have seen it in your textbook, but it might be like, what is the meaning of all these ones? But the main purpose of this stuff is actually to try to create a universal standard where everybody can be able to speak the same language. So now if I tell everybody, we want to cook something now, we will use 2 cups of rice. If you know what a cup of rice is, you'll be able to follow along. If I was trying to do a live cooking session on this call, if I said, okay, now everybody get your weighing balance, weigh 3 grams of salt, everybody can be able to get almost the same result if they are doing exactly the same thing. So that's the same purpose that SI units are for. They are just standards that would help people be able to understand it. So these SI units, would I say they are key ones that are the main units that we carry. Kilogram, that's for mass. There's actually mass, length, time, and temperature. I mentioned in a very important that you should take note of them. Mass, length, time, and temperature. So in chemistry, basically, these are the things you'll be mostly seeing. If you think through all the calculations you've done in chemistry, there's always going to be something that is related to mass, something that is related to length, something that is related to time, and something that is related to what they call it. What's the last one I mentioned? Time, length, I'm sorry, mass, length, time, and temperature. So just think of any formula at all or any SI unit in chemistry. You see that it always have one of these. If you want any extra, you would say mole or number of moles. So these are units that they have a standard measure that everybody around the world can be able to understand once you. So now, mass now, the universal measurement for mass is usually kilogram. Usually kilogram. There is kilogram, there is gram, there is milligram, there is centigram. But now, the one that everybody understands or that is most accepted is kilogram. So the universally accepted measurement for mass is in kilogram. Universally accepted measurement for time in seconds. You can measure time in hours, you can measure time in minutes, you can measure time in days, you can measure time in years, but the universally accepted one is in seconds. So time is universally accepted in seconds. The same way we go for temperature, the universally accepted unit is in Kelvin. So all these are just the purpose of helping to get accuracy and precision. So now, when we say, okay, I want to measure 5 grams of something, if someone is trying to measure it on a weighing balance, if you've seen a weighing balance before, it reads like what we can see in this top, this is our top right corner. You see what a weighing balance look like. You drop what you're trying to measure. If you've used it before, you notice that it reads both in decimal point and in whole numbers. So now, without you being conscious of the decimal point side, you would experience what they call error. So now, if you notice from your textbook, whatever textbook you're reading, after they talk about system international unit or that SI unit or basic units, you will start seeing them talk about errors next. So the reason for these errors now is the reason why they talk about errors is because you know that they are universal units, but now anybody that does not know well, know that those points, those decimal points can be critical. So there's a measurement that you might be trying to make that these decimal points will determine the level of your error, your level of your error. So those errors now, decimal points actually to help in measuring error. And these errors could be relative error, they could be simple error, they could be different types of error. But generally, that's the purpose of error. So now, these units, as I said, they have SI unit. Aside SI unit, there is also the CGS units. So I'm trying to be fast because we are trying to go. We have a really long way to go. So we have SI units, we have CGS units. That's where we have centimeter, gram, seconds, and stuff like that. So all these different units, their purpose, if you remember, you have been following me so far. Their purpose is to just achieve one goal, to have a universal understanding of a particular measurement you're trying to measure, so that anybody can say, measure so and so a particular compound, and you will be able to get exactly the same thing. So they are what they call fundamental units and derived units. So fundamental units are those ones that I just mentioned, mass, length. Those are the basic ones that every single measurement are usually hinged to. So let me see whether I can give an example. Everybody knows that it's always made from thread. Some thread might be polymer material, some threads might be cotton material, some threads might be polyester material, but we know that everything is made from, if we should go down, aside thread, they are made from plants. So that's fundamental thing that every cloth will be made from. It's just how fundamental units are. So every other units are going to be a combination of different adjustments of these fundamental materials: mass, length, time, Kelvin, number of moles. So every single thing will be either an aggregation of these stuffs, or just picking two, or picking one, or picking five of them and bringing them together to form a new unit. So this kind of thing that are a combination of several other fundamental units are called the derived units. So I believe this is supposed to be general knowledge to most people that are doing chemistry and also doing physics. You should have heard of fundamental units and derived units. So I'm spending some time here. So now, I was talking about error now. Errors could be measured in terms of significant figures. So you would see where they would ask you for, they will tell you to, if you solve something, your answer might be correct, but because of you were probably working with maybe decimal places, sometimes you might be working with 3 decimal places, just isolate all of them. You know, you don't have a constant number of decimal places where you make your measurement. You might get the wrong answer, and it's very bad for you. If you're trying to solve in your exams, it's best that if you want to solve, I would always advise to use decimal places. If you have decimal, I would always advise to use 2 decimal places, or at worst, if you're not using 2 decimal, use 4 decimal places. 2 or 4 decimal places. For better convenience, use 4 decimal places. So if it is within 4 decimal places, that's good. But if the thing is not that long, just preferably use the 2 decimal places. So why are we doing this? To prevent errors. So this is why sometimes you would solve and do not see your answer in the option. So I'm mentioning this because yes, it is in chemistry, but sometimes they don't really tell how important this thing is. So my advice is use 2 decimal places when the reading is small. But if you are seeing longer digits in the decimal place, use 4. That way you'll be able to avoid issues where you would solve, but your answer is supposed to be in the option, but you can't find it. Someone that solved and probably got something like 14, the answer is seeing something like 15. They'll be like, the answer is not here. But the reason for that error is because maybe you were solving with decimal point, not round off, and for that reason of round off, you happen to experience error, some level of error. So that's why we're addressing that. I would advise that you should do that to be able to avoid the kind of error they call random errors. So these random errors are the ones that comes as a result of bad calculation. When you make mistake of calculation, you were making issues with the decimal points, you would experience random error. But there's another type of error that can happen, which they call systemic error. So systemic error on the second hand is now the kind of error that happens when you have something like you are using a faulty material. That one is not really your problem. It's not really the person that is at fault. So systemic errors that occur when the material is bad. Systemic errors that occur when the material is bad. So you can put this in your objective question. They could ask you, and a user made a measurement of 4.5, but found out that the real value was, say, 4. This error was caused by the system. What kind of error? You might start seeing something like absolute error, random error, percentage error, systemic error. The reason for this kind of error, if you can think of the question and reason that, okay, this error was caused by the instrument, not by the person, or not by approximation, that particular kind of error is called systemic error. If you look down in my lower, I'm talking about, that's the portion I'm looking at. we have systemic error. This is what error is caused by the material you're using to measure. So if your ruler is bad, maybe like as me, you're trying to measure with your ruler, and that ruler, the people that made that ruler, those small marks, they did not measure it very well, and I'm getting a wrong reading. The error is not from you that measured it. The error is from the device. So that kind of error is a systemic error. While absolute error is kind of error that occurs when you're trying to round off stuff. Round off stuff to maybe to the nearest decimal, or and the real measurement is supposed to be something different. So those are the errors that occur when you're trying to measure. I don't know if anybody has any question for me for now.
Please can you come on random error again?
Okay. Random error is the kind of error that happens when you are the person that make the kind of error. Maybe you are trying to measure something, then you shake. You're trying to pour, maybe you're trying to, or let's say you're trying to use ruler to draw a line or measure something. Then as you are trying to mark one point, then to mark next, your hand shakes somehow, you now mark a wrong point, but you did not really notice. That kind of error is not that the ruler is wrong. The error happened due to human's inefficiency, your own mistake. So that's how random errors are. Random errors are errors that are caused by the person.
Okay.
Do you understand that? It is
How about
caused by the
relative
person.
error? That's like relative error.
Yeah, the relative error, I will still explain that. I've just explained systemic error and I've explained random error. Systemic error is one that is caused by the device you're using. It's not your fault. Actually, we are very cautious, but the device you're using is wrong. Maybe you carry a thermometer to measure your temperature. You think on it's now, I don't try speaking. You're trying to measure your temperature, and you then see 50 something degrees Celsius. You're not like, Jesus, I'm not feeling fine. Well, actually, you did not read that the thermometer is bad. You then go to the doctor and say, you are fine now. You say, but I measured my temperature and it was giving me something. That one, it was not your body that was bad. It was not you that was reading the thermometer wrong. It was the device that was wrong. So that is the systemic error. So now, if it is probably saying you were trying to weigh something, let's use weigh. Let's say you are trying to sell. Would I say what? Someone's mic is on. Let's say you're trying to sell something like chicken for someone. Maybe somebody somebody
Hello.
came. You have a chicken food store. You have a frozen food store. When I want to buy 3 kg chicken or 3 kilos of chicken, you now start measuring. You now cut excess. The balance, the scale is now shaking. Your eye, maybe like all these people that probably have not them, but maybe they have this kind of eye deficiency. Maybe they have either short-sightedness or long-sightedness or one eye defect. And they now, the thing is on 3, but their eye is not seeing it on 3 yet. Now still put extra. It's in that shit 3. They now say, okay, it's 3 is okay. While they're actually more than 3. So that kind of error is not that the device is wrong. It is the person that has error. So that kind of error is a random error caused by just the person. So then when you now go to
I can't hear you well.
always cost from absolute error when you're trying to how value is the absolute error. I don't know if I communicated there. The difference between the original value and the real value is the absolute error.
Okay.
You're not talking about that error. You're not trying to calculate it specifically. So that exact distance between, let's say, the person wanted to measure 3 kg, you now measure, say, 3.3 kg. The difference between 3.3 kg and the 3 kg that the person wanted to measure is 0.3 kg, and that 0.3 kg is the absolute error. So now, relative error now is now when you're now trying to change that absolute error in terms of percentage. Like in terms of how many percentage of that absolute error it is from, like now, got 3.3 now. The absolute error is 0.3. So now when you compare that absolute error to the original value, try to compare the absolute error to the original value. Now talking about the relative error. You have to check how bad was the error compared to the original value. So that what relative is. Imagine now, let me see an example now. I say, everybody, tell me what color it is, and I drop a black material. Then someone says, this is black. Or another person says, okay, this is black. Different black colors now. So to know who is farther away from the real black that I'm talking about, you need to carry that particular black that is bad, or the black that is not really black, and compare it to the real black that we're talking about. That's why somebody will say it's blacker than the other one, those kind of stuff. You can only get the difference or the relative error between two black colors when you compare it with the original black. So that's how relative error is. So relative error, the formula is always to check the real absolute error, in this case of 3.3. When you do 3.3 minus 3, you will get 0.3. That is the absolute error. So now to get the relative error is now the real value is 3. So 0.3 is absolute error. So to get the relative error, you say 0.3, which is the absolute error, over the actual value, which is 3. Then times 100 can now give you the percentage relative error. So relative error is always when you now bring the original value and divide the error by the original value. I don't know if I'm making any sense at all.
Okay. I don't know.
Sorry, can you come again? Sorry.
Okay. Relative error is when you're trying to compare the mistake made to the original value. Like, let's just say now you go to filling station now to buy fuel. Now, let's use that as an example. Many of us have gone to filling station to get fuel. Somebody now you wanted to sell, you say I'll buy 4 liters of fuel. Then the person that pumping the fuel now was now dancing, now got to make mistake. They did not type, they did not put the exact button before. They did not use button to type the exact amount you want to measure. They'll be putting the fuel and they'll be looking to see when things reach that value. So let's say the person is using that kind of method. He's pouring the fuel. His mind now went off. He now pumped, instead of your 4 liters, the person now pouring 4.3. What kind of error is that? Is it a systemic error or a random error? Somebody should tell me in the comments. Somebody should tell me here. Is that kind of error a random error or a systematic error?
This is
A random error.
Random
random error.
error.
Random
Thank you. If you say random error, you are correct. And the reason why it's a random error is because the machine was not bad. It was the person that just made a mistake and overpumped. So if you got that, means that you're following. The issue was because the person that was measuring made the mistake. That's a random error. So now, to now calculate the error, that's, if I say error, I'm still talking about, I can say error as absolute error. So the difference between error and absolute error is that you remove whatever is minus or plus, you remove the minus or plus, just put the normal digit. That's when you're talking about absolute error. Just error. The error between that person that pumped 4.3 liters when you want to get 4 liters, the real error, the error that person made is a 0.3 error. Why? Because the person pumped 4.3 instead of 4. So 4.3 minus 4 would give you 0.3. So the error that person make is 0.3 error. A 0.3 liter error. So that's the error that person made. So now to check if the owner of the company, if the owner of the what they call it, the filling station, how you made that kind of mistake now? How can you now see how bad the person did compared to what you wanted to sell, or how much they cheated their self. They will now check that 0.3 divided by your 4 liters. They will now see how many percentage extra they've given you. So they now want to charge you extra for that. That is how they can use to get the amount that they will charge you extra. So when they say 0.3 over 4, whatever they get, they multiply by 100. They will know they pump that amount extra for you. So that's how they get relative error. So you check the real value you wanted to pump. Just if you get an example and you want to know how to calculate your absolute error, just say, okay, what they are saying now, what was the actual value? They will always mention it in question. They will always mention the actual, and they will mention the error, the one that has mistake. So to get the one that has mistake, to get the error, you just check the one that has mistake minus the one that has the error. You get the absolute error. Then now to get the relative error, that value you got from your error, just divide it by the one that is the actual value. you get your relative error. I don't know if I'm making any sense at all.
Yes.
Okay, so that's for this now. So that's basically what when you're talking about measurement in this chemistry, these are the topics that the things that will bring into your when you're solving portions that are talking about measurement, we're always talking about SI units. And when you talk about SI units, you should know that general units that is accepted. And there are two types. There is the derived one and there's the fundamental one. So once you know there's the derived one and there's the fundamental one, you know that the derived ones are the ones that are gotten from the fundamental ones. That's the combination of the one. So while what we call it, and once you do those now, there are now possibilities of error when you're measuring. And the kind of error that could happen is either a systemic error or a random error. Systemic random error. So once you've gotten the type of error it is, you can then calculate error or whether it relates. You can get the error. Once you've told relative error, you can get for random error, you can always calculate the absolute error. For systemic error, you can always calculate the absolute error. So, but if I would say how it is there are two key types of errors. There are two key types of error. Either an error caused by you or an error caused by the machine. So not only you, the error is caused by you or your environment. That's the same thing. So in the environment usually follow. So under the random error, environment is among error that is caused by the environment. Maybe the environment is too hot. You now try to measure something, thing was not giving you something. That one is part of random error. When it is something that is caused by the machine itself, that's a systemic error. Communicating sharp. So let me just, before I move to the next slide, let me talk about this thing that is here. We see accuracy and precision. Accuracy and precision. This is something that can be very, very confusing. If you don't really know, if you don't really pay attention to it, you will see it in the exam. You most likely, it has a chance of it's 5%. It's 5% probability that you will see questions on precision and accuracy in your exam. I can guarantee you that from my analysis, I've seen that it's 5% probability. You always see questions on precision and accuracy. So now, how does this kind of question come out, or what do you need to know about accuracy and precision, or what will make it clear for you? Accuracy is just when you are, before you can say something is accurate, before you talk about accuracy, there has to be a real value. You know the original target. Like now, you can, everybody should just close their eyes and pump fuel. Let me use that same fuel analogy again. Everybody should close their eyes and pump fuel. Liters. Or I don't know if people have seen that trending video where they will show two people that they are trying to time seconds. They will not say, okay, give me 3 seconds. Then they will not say, do not see the timer, you just face back. The timer will be facing the audience or the camera. Then trying to stop the watch will now be waiting. Okay, they say 2 seconds. And I'm like, stop the machine. So now they know that the accurate value, if you're accurate, you are going to be getting 2.0 seconds. That's what you're targeting. So now, when you know the exact value you're targeting, you can check someone's accuracy depending on how they were from that accurate, that exact value you're trying to target. So now let me take another example. Here we like arrows, or we usually use gun. I don't know how many people would like to use gun, because I think I would love to try to shoot a gun. Let's say we now go to probably shoot a gun now, or we go to where they train to shoot guns. They now give us the bull's eye target. Okay, everybody, our target is to get the center. The target is the center. Now we now have the target now. That's the standard value we're trying to target. So now, if you shoot and you are probably close to the center, you are slightly accurate. You are close to accurate. If you are far from the center, you are not accurate at all. Your hand is not straight. They will say your hand is not straight. Or let's say an example, shots on target for football. If you fire towards the post, if your ball hits bar, hey, it didn't enter the post, but you are close to accurate. You are close to being accurate. But if your ball, you post target the post, you are firing ball towards the corner. They cannot even catch that shot on target. So accuracy has to be with a target. It has to be for you to say something is accurate. So then now, precision now is now when somebody continuously hitting the same spot, whether it's correct or not correct. If you're hitting the same spot continuously, you'll say, this person has strong level of precision. So now let's say somebody now, let me use that same person that has eye issue. Maybe someone, I'm not trying to demean anybody. If you have probably for any reason you have an eye defect, I'm not trying to say something bad about you. I'm not trying to bring a level of understanding to everybody, so everybody will get the picture, because we are here to learn. So now, for people that have eye defects, if they're not already with their medication or with their treatment, if they don't take their treatment, and they try to shoot a gun on target, in their own eyes, they will see that they are putting the gun to the right position. But when they shoot it, it will be in another direction. So for someone that has high level of precision, and the person has bad eye, the person is shooting the same point, but it will be far away from the real. So the person shot the first one, he hits. Let's say they're trying to get on point 1. The person shot the first one, he hits point 3. Hey, far away from the targeting 1. Shoot second one, point 3 again. Guys, shift your hand now. You know the enter 1. Shoot again, point 3 again. The person has high level of precision. It's not accurate. Because why is it not accurate? Because the target, your target is 1, but you're shooting 3, so you're not accurate. But precise, because your targets are always hitting similar points. But someone that probably they say, okay, the target is still 1. The person shot the first one, he hit number 3. Second one, he hit far number 10. Then he now hit the last one. He got the last one, number 1. The person's values are scattered. 1, 3, 10. It's scattered. The person is not precise. But the person had an accurate shot. He had one accurate shot. That is one shot that hits the target. So now, he has to do with a target, while precision has to do with how close your attempts were to themselves. So if you made 3 shots and they hit bar, all of them hit the same bar, you had high precision, but you're not accurate. But if you made, let's assume you took 5 penalties. You took the first penalty, you hit, hey, remain small. Second penalty, bar, hey, remain small. Third penalty, bar. Your 5 shots were bar. You have high level of precision. You are close to the target. That's the goal post. But now, somebody that the first penalty event was throwing, second penalty, corner, third penalty, over the bar, fourth penalty, the person was accurate, but was not precise. Though he was not precise, he was accurate. He was able to hit the accurate target. He was not precise. He had scattered attempts. I don't know if the picture is getting clearer to you guys.
Yes.
So that's actually the difference between precision and accuracy.
Please
Accuracy
come
has to do
again,
with targets. Okay. Precision is talking about how close your attempts are to themselves. How close your attempts are to themselves. While accuracy has to do with how close you are to the target. So when you're talking about accuracy, you need to just be correct. You need to be correct. When you're talking about precision, you just need to have similar target, like your attempts should be close to themselves. Be close to themselves. So if let's assume everybody want to grade somebody, we say, okay, the guy, all his shots were hitting the bar. The person was precise. So if the measurement is precise, we're not talking about whether he score or he didn't score. You're trying to target post, but you're always hitting bar. You're always hitting bar. The person was precise. But now, if what we're saying leave precise, we're looking for who score. The person scored 1 goal out of 5 shots. Even if other of his shots were outside the bar, over the bar, or it never even hit bar, that person would be said to hit the target. That person was accurate on 1 shot, but was not precise. But the person that was hitting the bar continuously was precise, but not accurate. I don't know if I'm speaking English.
Yeah, we understand.
Okay. Thank you. So now let's move to the next portion. We will be looking at moles now. We'll be looking at moles now. So mole, when mole is another part that I can say is kind of complex in chemistry. It's kind of confusing somehow, but it's actually simple. But to be honest, it's simple. So this word makes students, it makes students, moles, M-O-L-E-S. It makes students freeze most of the times. I remember when I was trying to learn chemistry, I was not in school when I think I was of mole when I was in secondary school. So at the time when I came to school, it was just like as if Jesus is happening. Everybody was nodding their head, even people that understood them, they didn't understand. They were nodding their head. But me, I was like, when did they start? What is mole? What was all these ones? It was confusing. But I got to a point where it became I kind of understood the full concept. I don't think there's any question that anybody would ask me on the mole. That's straightforward, numbers, except maybe I make a kind of slight error or missing error. I'll try to use that view to try to explain how mole is. So first off, I know that this word of mole, it can make people just be scared, and it can be complicated somehow, but it's actually very simple. In simple terms, it's just a specific number. When you hear the word mole, you're talking about a specific number. So that specific number is just when they tell you a mole of something or 1 mole of something, it simply means 6.02 times 10 raised to the power 23. Simple. A mole of something is just 6.02 times 10 raised to the power 23. So take this number in your head. That number is Avogadro's number. So if you're writing or if you're jotting something down, just know that a mole, just write mole.
Mole is what?
I can hear you.
6 point.
Mole is equal to 6.02 times 10 raised to the power times 10 raised to the power 23. Not minus, times 10 raised to the power 23. So mole is equal to 6.02 times 10 raised to the power 23. And in simple words, if I was writing it on the board now, I would say mole is equal to 6.02 times 10 raised to the power 23. And it's also equal to Avogadro's number. Also equal to Avogadro's number. So if you hear 1 mole of something, just know that they're also saying 6.02 times 10 raised to the power 23. And also know they're also saying Avogadro's number. So every mole, every single mole, 1 mole is Avogadro's number. And what's Avogadro's number? 6.02 times 10 to the power 23. So put this one at one corner of your mind. Put that one corner of your mind. See it here. If you look at this spot on my screen now, you look at this spot on my screen, I said a mole is Avogadro's number. That part, they said 1 mole is equal to 6.02 times 10 to the power 23. So on another word, the reason why mole, I can say mole is complex because they give it plenty names. Only mole is 6.02 times 10 to the power 23. Only mole, number. Only mole also is 1 dozen of carbon. That is 12 carbon. So that idea of reducing carbon can be a bit confusing. So we know that when somebody says a dozen, everybody kind of knows a dozen of something is 12. Share. That is the same way we say 1 mole of something is 6.02 times 10 raised to the power 23. As we know that like as we know, 1 hour is equal to 60 minutes. That same way that 1 mole is equal to 6.02 times raised to the power 23. As we know that 1 day is equal to 24 hours. That is the same way we know that 1 mole is equal to 6.02 times 10 raised to the power 23. So this thing is just like a measure of something. A mole is a measure. Some people like a mudu. People in Abuja, they usually use mudu measure gari. I don't know, but I heard that was used. People in Nigeria, people in Lagos, they use derika, 1 derika. People in maybe in the east, where I schooled, they use. I don't even know why they call it just cup, but they use cup. When I went to the east, I was wondering. I said, I want 1 derika of rice. They were just looking at me because I grew up in Lagos and I schooled in the east. I said I want to buy 1 derika of rice. The lady was like, derika, like from where to where? It was confusing. But someone in Lagos, if I said 1 derika of rice, they would definitely understand what I mean. So just how it is. When you don't understand what a mole is, once you know how many a mole is, it can be confusing when they tell you how many atoms are in a mole. So the number of atoms in a mole is 6.02 times 10 raised to the power 23. The same way you can tell that the number of something in a dozen is 12. That's just how it is. It's as simple as that. It's as simple as that. I don't know if anybody has any question about what I just said so far.
Sir.
Does anybody have any confusion about it?
Yeah.
Okay, so now I haven't established that background now.
You say?
Haven't I was asking when anybody had a question. So I'm believing that now everybody understands how a mole is. Now you've gotten a picture of a mole is. A mole is like 1 cup of gas. A mole is like 1 America of rice. But now in case of atoms, now that's where they use it now. So they say, give me one mole of an atom. It means give me 6 times 6.02 times 10 power 23 atoms.
Who should on off their speaker? I can't hear very well.
So please, if your mic is turned on, please just take it down because everybody is trying to pay attention. So as I was saying, if somebody told you 1 mole of something, just know that 1 mole of something is 6.02 times 10 to the power of 3 atoms. So when every time you've seen 2 moles of carbon, 3 moles of carbon, if you were in the what they call chemistry world, that's what they use and buy Gary. I want to buy one mole of carbon. I want to buy 3 moles of this. So everybody's like, okay, if you say you want to buy 1 mole of carbon, they will measure 6.02 atoms of carbon times 10 to the power 23 and give to you. If you say you want to buy 1 mole of sodium, they will measure that amount of atom and still give to you. So that's how it is in the picture or in the group of atoms. So that's just the idea. So now, when we look at atomic mass now, the
I have a
okay,
question on Jesus.
ask your question.
Does it mean that, for example, now 2 moles of calcium will be equal to 2 times 6.02 times 10 raised to the power 23?
Bam. That's it.
Okay.
Would understand that times 10 to the power 23 atoms. That is the number of atoms in 2 moles. Whatever the answer I give you is going to be number of atoms in 2 moles. Okay. He asked a question that if somebody said 2 moles of, I've forgotten it, I think he said sodium. 2 moles of sodium is equal to 2 times 6.02 times 10 raised to the power 23. So yes, that's what it means. Now 6.2 times 10 raised to the power 23 what? Atoms of sodium. Atoms of sodium. So we're saying 2 moles of sodium. So it means in sodium now, 2 moles of sodium contain 2 times this particular Avogadro's number of atoms.
Are you still going to talk about the concept, like the concepts under moles, like the molar mass, the number of moles, how to calculate them?
Yes, we are getting there. We are getting there. It's one step at a time. I'm just trying to build the foundation so that when we move forward, nobody will get confused. So I've talked about moles, I've talked about Avogadro's constant. So everybody's supposed to be able to know now when I say Avogadro's constant, you're supposed to know Avogadro's constant is the universal number of atoms that is inside 1 mole.
Please, just
so that's just how simple it is.
Skipping.
I think I don't know. Can anybody hear me clearly, or is it only
I can't
me
hear
that
you,
I think
sir.
my mic is clear? I don't know.
I can hear you.
Sorry,
I can hear you.
probably
I
your,
can
I can hear
see
you.
you. I can actually
probably
hear
your
you.
network. The person that is complaining. The person that is complaining. Probably your network
I
is
can hear you.
okay. If you can hear me, good. So now, as I was saying now, I haven't explained what moles are now. The next thing I'm talking about is now we said moles has a particular number of atoms. So now, what is now atomic mass? Mass now is now when you talk about atomic mass, would I say it is the total number of subparticles in a particular atom that makes the mass of a particular atom. The total number of small particles, and not just any kind of small particles, a specific kind of particles, which I will explain what they are. So atomic mass now is talking about.
Are
Can
you
you hear
talking
me?
about atomic mass? Are you talking
Yes,
about
I'm talking about
atomic
atomic mass.
mass?
Yes, now,
Okay, what is
yes.
atomic mass?
So yes, I'm talking about atomic mass.
Simple answer question, Jerry.
I did not get your question. Get your
Probably she's
So you
having network
said
glitch on her.
is the total number of small particles.
Yes, the total number of
Hello?
subatomic the total number of small particles. Let me use simple English. Atomic mass is the total number of small particles that make up the atom.
Okay, thanks.
So now, let me now bring it down. So we are looking at a mole, and we said the mole contains plenty atoms, up to 6.02 times 10 power 23 as a mole. So now, we've now this mole, we have now gone deep now. This atom we're talking about now, atom now, how can we now know the mass of that individual atom now? How can we now know an atom? We left mole now. Mole is is when you talk about plenty atoms. We're talking about the mole. So now let's leave plenty atom. Let's now focus on one atom now. We are zooming in now to just one atom. So one atom now is made up of other subatomic, other small particles. And every atom is made up of 3 key particles. Every atom is made up of 3 key particles, and that's what I'm calling the subatomic particles. So these 3 key particles are proton, neutron, and electron. Yeah, proton, neutron, and electron. So these are the 3 key things that make up an atom. So if you look at, if I should go back, if I step backward, I'll say a mole is made up of plenty atoms. An atom is made up of proton, neutron, and electron. So an atom is made up of small particles too that they call all these proton, neutron, and electron. Now, these proton, neutrons, and electrons are now of different kinds. They are different kinds of particles. And if you are already someone that has probably tried to read it ahead of that people, or try to read, you have tried reading, you have heard they said proton is positively charged, electron negatively charged, neutron is without a charge. You get confused about this thing. Just use proton and neutron to tell. Proton has plus, that is positive, that is P for positive proton. N for neutral does not have charge. N for no charge, N for neutron. No charge, neutron. Positive proton, that is PP, positive proton. So then the last one, I don't know why they did not give it N, they did not give it the name that has, maybe because of neutron or yeah, but electrons are negative charge. So once you have dealt with positive, you have dealt with no charge. The next one that is going to be is negative. So the one that is negative electron, you can remember that positive is for proton, neutral is for neutron, and negative is for electron. One is negatively charged. Now,
Yes, proton is positive, electron is negative,
yes.
While neutron is neutral.
Yeah, neutron is neutral.
Okay,
so now we're trying to talk about atomic mass. I started talking about these things. So now, why are we talking about this much? Because an atom now, it has a mass. Atom has a mass. So that's the atomic mass. So now, the things that make up this atomic mass of an atom. So now we say that there are 3 things in an atom. 3 things that make up an atom. 3 particles that make up an atom. So an 3 particles is proton, neutron, and electron. Now one of these 3 is short 1. One of these 3 particles is short. This does not contribute anything. One of these 3 does not contribute anything to the mass of an atom. And that does not contribute anything to the mass of an atom.
No.
Can you hear me? Can anybody hear me?
You said proton is positive, electron is negative.
Yes.
What was this thing? The neutron.
Yeah, okay.
Hello,
If you heard me, I can hear you. Just turn off your mic now. If you can hear me now, just what I said, the last thing I said, for proton is positive, neutron is negative, electron is negative, neutron is neutral. Sorry, don't know what I just said now. Proton positive, neutron negative, electron. What did I say? Proton positive, neutron neutral, electron negative. I beg you. Proton positive.
I have a question.
Okay.
Dad, the nucleus of an atom is it also proton, neutron, and electron?
The nucleus. Okay, we are getting there. So that's what I was about going to.
Okay,
so now we talked about, we know that atom is like, let me see an example of something that we would call an atom. So now, since we are using food, now we're talking about food. Everybody knows that when we buy tomato, all those pork, the stick that is on tomato and even pepper. No, in Nigeria, we don't use stick on tomato. Let me use it because at pepper we use that stick. When you carry pepper, among the useful something in pepper, that stick is not among. Most of the time, people would cut off that stick, throw it away. That's how electron is. Electron does not contribute to the useful mass of an atom. So when they're talking about who has been helping atom have a body, who has been contributing to. So if I want to make a funny scenario, I'll say electron is a useless boyfriend. He does not have anything he's contributing to an atom. Atom is the girlfriend, but she has 3 other boyfriends. Neutron is one of the boyfriends. Proton is another of the boyfriend. Electron, negative charge, they contribute anything. -1 and B. So electron is not contributing anything to mass of an atom. Atom is the fine girl. So due to that fine girl that atom has, electron does not contribute anything to it. It's only the boyfriend proton and the side boyfriend also. I'm not trying to encourage any boyfriend to beg. Encourage anybody to have any boyfriend. I'm just trying to use this as an analogy because I know this is something that everybody can be able to understand since we are all young. So electrons contribute anything to the atomic mass. Electron.
Please off your mics, please.
So can you hear me now? Okay. So what I was saying, electrons contribute to the weight of the mass of an atom. But proton and neutrons are the ones that are responsible for the main mass. So now, when we now talk about the atom now, I know that somebody was asking a question about nucleus. So now, what makes the nucleus of an atom? I already told you guys already that atom is made up of 3 particles: proton, neutron, and electron. So if you wrote in your book, just cycle proton and neutron together. Cycle proton and neutron together. Cycle both of them together. That cycle of both of them together is what we call the nucleus. So the nucleus is a combination of neutron and proton. The nucleus of every atom is a combination of neutron and proton. The nucleus of every atom is a combination of neutron and proton. So now, when you talk about nucleus, it's the combination of neutron and proton. That's what makes the nucleus. And this nucleus is what is the reason gives the atomic mass. So I already told you guys, those are the contributors. So now that union is what they call the main thing that is responsible for the atomic mass of a particular atom. I don't know if I complicated anything or if anybody understands what I'm trying to explain. Am I clear? Or is anybody confused?
Yes, sir. Yes, sir. It's clear. It's clear.
100. More than
Okay, so let's go on. So now we've looked at it now. We now know what a nucleus is. A nucleus is a combination of proton and neutron. We now know what's responsible for the mass of an atom. Neutron and proton also. We now know that electron contributes to the mass of an atom. So we know that atomic mass is the sum of the total number of neutron and the total number of proton for a particular atom. So that what gives you the atomic mass. So if you take the atomic mass of a particular species, you just know that you add the total number of proton and the total number of neutron. Is it clear?
Yes, sir. Yes, sir.
Okay. So now,
Yes, sir.
So we talked about that now. We talked about atomic mass. And so there's now something that now happens sometimes where every atom has a unique number. Every particular element. Let me use element now. So an element is a type of atom. So there are different types of atoms, and those different types of atoms and the number. There are different types of atoms and the number of protons. So every different kind of atom. I know how that is now. We know that atoms are made up of protons and neutrons. So now, as the number of protons increase, that's how we move from. That's how new elements are formed. When you increase the number of protons, you are forming a new element. Every new number of you add. Let's start with hydrogen. Hydrogen has one proton. That's the beginning. Yes, one. Everybody has one. The thing has one proton. But now, when you add one more proton to a particular atom, it ceases from being hydrogen. It becomes helium. When you add a proton again, it ceases from being helium. It becomes lithium. When you add another one, it ceases from lithium. It becomes beryllium. So that's how we get different elements. Different elements are formed from the different number of protons. Different number of protons form different elements. Different number of protons form different elements. So now, as you increase the number of protons, the elements vary. So now, everywhere you see what they call it. Let me see. Everywhere you see hydrogen, as long as it's hydrogen, it will definitely have only one proton. Everywhere you see helium, it will always have two protons. If it does not have two protons, that means it's definitely not hydrogen. It's definitely not helium. If it has three protons, it is definitely lithium. You cannot see any lithium more than three protons. If it crosses two protons, if it crosses three protons, it can never be lithium. It's going to be another element. So this number of protons is what tells what element it is. The number of protons tells what element it is. The number of protons tells what element you are dealing with. The number of protons is always tied to the element. So now everybody should know that
Yeah, what is happening?
Calm down.
Network is bad here.
carbon has 6 protons. When you see with check now carbon, you check, you count the number of protons. You are seeing an
So your network is breaking.
isotope of carbon. So the isotope can form. Is my network clear to you?
It's not clear. No.
Your network is bad.
Your
Network is
network
bad.
is very
No, sir.
your network is breaking.
Your network is breaking.
It's okay. Your network is bad.
Yeah.
Let's get them.
So whose network is bad?
You. What
Can anybody hear
joining?
me?
They don't allow me to see road. Am I here? Your network is cracking. It's breaking. I can't hear you.
Sir, let's continue. I think it's fair now.
Hello, sir. Can you hear you?
Can anybody?
No, it's still breaking. No.
Yes.
It's
Yes,
still breaking,
let's
but
Yes,
it's
yes,
clearer
continue.
now.
We can hear you.
We can hear you now.
and let's continue.
Let's continue.
Yes, you can.
Okay, so where did you guys hear me clearly last?
You
Carbon.
said carbon has an isotope.
Okay. When I was talking about carbon, okay, better. Thank God I was not far. So I was saying when everybody sees carbon, we know that any atom that has 6 proton is carbon. So now when you now see carbon seems to be fatter or slimmer, because everybody knows carbon is 6. But now we know carbon, we always know carbon to have a weight of 12. Is weight, if you go to weighing balance, it has a mass of 12. But now if you now see carbon now it's looking fatter. Why is it looking fatter? You want to confirm whether it's really carbon, you check how many number of proton is there. Still 6. It means carbon has formed an isotope. So an isotope is another version of carbon that is fatter than the normal size of carbon or smaller than the normal size of carbon. So when there is a change in the mass of a particular element, you have formed an isotope. I don't know if I made it clear at all. Once an element has a different mass specifically, you are forming an isotope. So isotope, in simple terms, isotope are elements that have a different mass, but it's the same element. So in some other place, they'll say the same mass number. I'm sorry, they'll say the same number of protons, but different mass number. Those are what isotopes are. So in simple terms, any element that has a different mass number from the usually known mass number. So let me use an example now. Everybody knows Superman to be wearing red and blue. Everybody knows Superman to be wearing red and blue. If for any reason you start seeing Superman wearing green and white, you start wondering, is that we don't know Superman to be like that. But now if you look at the person very well, you say, this is actually Superman. Oh. So that is the same thing. The number of protons can always help you identify the particular element. But now the mass number can change. It's like the clothes we wear. The clothes we wear can change. But the normal main person does not change. That is the normal number of protons does not change. So what usually causes the change in mass number is when the number of neutrons either increases or decreases. So we know that what is responsible for mass is proton and neutron. So we said proton is stable. Proton don't change. In the stand still. But now neutron can either reduce or increase. So when there is a fluctuation in the number of neutrons, that's when you form isotopes. When there is a fluctuation in the number of neutrons, that's when you form isotopes. So when there is an increase in number of neutrons, it will increase the mass normally. So, but to form an isotope of that particular element. When there is a reduction in the number of neutrons, it will also form an isotope. So I don't know if I'm communicating anything at all.
Yes, you are communicating.
Please,
Okay.
make that last statement, please.
I did not get what
When
you
there
said.
is
Someone said something. When there is an increase in number of neutrons, you would form an isotope. So isotope is always formed when there is either an increase or decrease in number of neutrons specifically. Isotopes are only formed when there is a change in number of neutrons. Isotopes are only formed when there is a change in number of neutrons. So that's just the idea of isotope. So now I've explained what masses are, what atomic mass is. I've explained what constitutes the mass of a particular atom and what happens when the mass of a particular element now changes. I've explained what an element is. An element is a particular atom that has a specific number of atoms of protons. So that's just it. So now if you should now go to what they call relative atomic mass, it is now when you have now seen, okay, carbon, today he has 12. His size is 12. Tomorrow he's wearing size 13. Next tomorrow he's wearing size 14. He's increasing in size. So now for you to be able to now say, okay, carbon is neither 12, is neither 13, in the change. Sometimes it go fast, sometimes it go slim down. So now to get an average kind of size that you can always tell that, okay, this is the average of carbon's weight. In weight, no, they always pass this place. It's always within this particular band. That's what relative atomic mass is. It's a kind of measure of the average atomic mass based on how many they are. I don't know if I'm communicating at all.
Yes.
Okay, so now let's that aside now. When you've understood these ideas of what protons are, understood what a mole is and all those stuff, you can now go into the calculations of stoichiometry because it's all this thing that would I say that they are the building blocks of stoichiometry. So where we are talking about molality and all those stuffs. So now, what is molarity? So as I was using that food example, molarity is the amount of a particular ingredient in food, in a particular quantity of food. So now I think we are trying to create we are trying to cook 2 cups of rice. If you put more salt into that rice, you are affecting the concentration of salt. That is the molarity of that rice. If you reduce the amount of salt, you are affecting the molarity also. So the quantity of salt, the concentration of salt in that food is what molarity is. Simply the quantity of a particular thing in a general stuff. So if I want to check the concentration of boys in this call now, I will check how many people are in this call. How many of them are boys? We can be able to tell the concentration of boys in this call, or be on this call rather. So that's how concentration is the quantity of a particular thing in the midst of other things. You get? So now in chemistry terms, they always say it is the number of a particular mole of something over the total volume of that particular thing in that. That's how you're trying to check the concentration of salt in water. Water is the thing they are trying to know that is the main medium. So the quantity of salt, to get the concentration of salt, you need to calculate the number of moles of salt in that thing over the total volume of water that is present. So concentration is simply number of moles over volume. Number of moles over volume. But now, not any volume now. The volume in liter or dm cube. So dm cube and liter are the same thing. So don't confuse yourself. dm cube and liter are the same thing. So when you see something dm cube, just put it in your mind. If you are always conversant with liter, just put in your mind liter. So if you let's assume you go to, I want to buy 3 dm cubes of fuel, they will laugh at you because they'll be like, who is this one? You've just come Nigeria. But when you say I want to buy 3 liters of fuel, the person that is attending to you, that is the attendant, would be like, okay, they will pump it to you. So, but either way, both of them are the same thing. dm cube and liters are the same thing. So just take down in your head. dm cube and liter is the same thing. dm cube and liter is the same thing. So now that aside, another thing that is here now is molality. So now, molality is how much of a particular thing is inside a particular kilogram. So now, molarity and molality, molarity, riti, and liti, R and L. R, that is molarity, is talking about volume, the amount of salt in a volume of water, while molality is the same amount of salt in a gram of water. Amount of salt in a volume of water, molarity, R. Amount of salt in a gram of water, molality, L. That's just the difference between both of them. One of them is trying to check the quantity of something in a liter of something. While the other one is checking the molarity. That's the first one. Molarity.
Yes, sir.
If you look at this, if you see this image here, we are trying to check the number of salt in a liquid, that is in liter. Number of salt in a particular liquid in liter. So now, on the other end, molarity is the same number of salt in a particular thing again, but now it's not in a liquid, now in a solid, in a kilogram of something. That's the difference between molarity and molality. I believe this image should be able to help you. Both of them are water. We have water in this cup. We have water as block. So when you're talking about the kilogram, number of salt in kilogram of something, we're talking about molarity, L. Molarity, number of salt in a liquid, molarity, R. You get? So now when you are now trying to do mole fraction now, mole fraction is now another concept that I'm talking about. Mole fraction is now talking about when you are talking about, sorry, give me a minute. So as I was saying, mole fraction is now when you're talking about how many, okay, when you're talking about how many of something
Yes, sir. I have a
is in the
question.
list of several other things. So now, as I was saying, that's boy versus girl something.
I have a
The
question,
mole
please.
fraction. Okay, I did not hear you. Go ahead,
So
I can hear.
can we say that molality equals to number of moles over volume, and like the volume will now be like kilogram? Is that the like if you want to solve for molality?
If you some people you will see it in some textbooks like that, but logically, volume is mostly related to liquid.
Okay.
mostly. But volume can be related, can also be related to solid. But for us not to get confused, some textbook would not use over V, but for kilogram. Say W, that's W for weight, because solids is what molarity is trying to check, the concentration of a particular thing in a gram of solid. I don't know if I'm
All
communicating
right,
anything
all
at
right,
all.
sir.
Normally, we know they don't calculate volume in gram, so that's why it is kind of improper to say number of mole or something over volume. And I'm saying in kilogram. Volume is not measured in kilogram normally, so it's not making any logical sense. Volume is supposed to be measured in liters. So to prevent confusion, you can say molarity is number of moles over volume, while molality is number of moles over weight. Number of moles over weight. So that way it will be clearer for you. You will not get confused.
All right, sir. Thank
So
you.
now, yeah, you're welcome. So now, mole fraction now is now when you have you're trying to now compare not in the entire liquid now or in the entire solid now. You're trying to say, okay, we are trying to check. You cook rice, you put beans, you put dodo inside. That's plantain. How many? What's the proportion of dodo to the rice and beans? You now count. Okay, how many grains of dodo is inside this thing? You count. Okay, there are 5 grains of dodo. Okay, how many grains of rice is here? Somehow, you magically calculate the number of grains of rice. How many grains of beans are in this thing? You calculate. You will now start checking. Okay, add all the grains of rice plus all the grains of beans plus all the grains of the dodo, and now divide it by the number of dodo that is there. You will now see how many, the fraction of dodo that is inside that thing. You now see how small the dodo is compared to the rice and the beans. You get? So that's how mole fraction is. It's trying to check everything now, count everything, then now isolate one. That is to get the fraction of that particular one. So now if you want to do the same thing, the mole fraction of rice, you will still add the total number of rice, total number of beans, total number of dodo. Divided, that is, rice will now be, the total number of rice will now be divided by the total number of dodo, beans, and rice. That way, I believe that should make sense. So you are trying to check a particular thing in the midst of order of his brethren. A particular thing in the midst of order of his brethren. So you count, okay, let's see who is the richest person here compared to everybody now. Sometimes they will like, okay, let's see. How much do you have? I have 1,000. How much do you have? I have 2,000. How much do you have? I have 3,000. Okay, let's see who is contributing the highest now. That's what you're trying to do with mole fraction. Who is contributing the highest? You now check. 1,000, if you compare 1,000 to 6,000, how many percent of is 1,000 inside 6,000? That was a fraction. That's the fraction that that person that has 1,000 is contributing. The person that has 2,000, how much is 2,000 naira? How much is 2,000 naira in the combination of that 6,000? That's how much the person is contributing to that money. How much is 3,000 to the entire 6,000? So the person that contributes 3,000 divided by 6 is contributing 60%. It's contributing, sorry, 50%. So the fraction of the person's share is 50% share. Of the entire thing. So that's what mole fraction can help you do. It can help you know the element in a mixture. That's what can help you tell. I don't know if you're still with me. I don't know if
Yes,
are you still
yes,
with me? Can you
yes,
guys?
yes,
Okay.
yes.
So now the next one we are going to be looking at now is it's about atomic structure. So I already hinted a little bit of
Hello, sir.
atomic
Sir,
structure.
hello, sir.
Yeah, I can hear you.
Okay, please, can you talk more again on this additional total number of? I'm confused somehow.
Okay,
Please,
so
on
let
the
me go
mole
back to that mole fraction.
fraction.
Let me go back to mole fraction again. So now let's assume now. Let me see you. Let me use a party, or let's say let's go back to secondary school when we're having red house, green house, blue house. You now stay. Okay, everybody is here in this school. How many students are in the greenhouse? Or how many students? How many? The greenhouse is how many percentage of this school is in the greenhouse? Let's assume there are like 10 greenhouse, 20 blue house, and 30 red house, 10 green house, 20 blue house, and 30 red house. So to check how many the blue house, the green house is compared to the entire school, you would add everybody in the entire school divided by the total, that you use the number of people in the blue house and divide the total number of everybody in the school. Blue house, but the total number of everybody in the school. Both red house, green house, add everybody together. It will tell you the quantity of blue house or green house that is in that school. If you go for red house, check the number of red house divided by the same total number of everybody in the school. That way, if you want to share something, you will not do it partially. You'll be able to know how many people are in the red house, how many people are in the blue house, how many people are in the green house. So that's what mode fraction is. It's trying to check the contribution of each unique component of a particular mixture. I don't know if it's clear now.
It's clear now, sir.
So, sir,
I'm okay.
like
Okay.
defining it in chemistry, like how are you going to put it?
It's just the same thing I've been talking about now. Let's assume they give you
It's
something
something
now.
I
Let's
did
assume they tell you find the mole fraction of let's say sodium. When sodium is, there are 3 grams of sodium, there are 4 grams of this one, there are 5 grams of this one. All of them should be in the same limit first off. Or let's say they even use mole. Since it's mole fraction, they say mole, they usually use mole. So we have sorry, we have 1 mole of calcium, 2 moles of potassium. Or let me just use something that is simple. 1 mole of A, 2 mole of B, 3 mole of C. Then I try to ask you, calculate the mole fraction of B. What the answer is just take B and put it, nail it on the cross, and put everybody on that to watch it. That's just a simple thing. Take the number of B, nail it on the cross, that's nail it up, and put everybody on that. Try to watch it. So that's how you do it in mass. So if you want to calculate it now, you now be like, okay, who is B? How many is B? B is 2. Nail it on the cross as you put it up. Then put every other people on that to watch it. So add everybody on that. So everybody on that is now A, B, and C. Add A is 1. Add B is 2. Add C is 3. So you now be having something that looks like 2 all over 1 plus 2 plus 3. So that's just how it is. 2 all over 1 plus 2 plus 3. If you wanted to do the same thing for C now, nail C to the cross. That is, take C up. All over everybody that is there to watch it. 1 plus 2 plus 3. Because they say you should nail C to the cross, does not mean that C would also not be down to watch. It's also be down to watch. So that's how it is. I don't know if it's clear now.
It's clear, sir.
Yes.
Okay, so that's for that one. That's for mole fraction. So now I was saying something about atoms. So now I think here you'll be able to understand with this diagram that you're seeing here. So now everything we are seeing here in this cycle is what they call an atom. This bigger cycle is an atom. Now what is moving around the atom? If you look at here now, this one looks like money. The electron. Electron is just moving around. The people that are inside the main office, the people that are inside the main office is positive on one side, negative on one side. So from what I showed here, I said we have positive. The positives are the chefs. What I said, the negatives are the people that don't leave the office. So the inside place is the office. So as we can see here, these 2 of them are in the office, the nucleus and the neutron and the protons. They are both in the office, and the office we are talking about is the nucleus. So the nucleus is what covers the proton and the neutron. The nucleus is what covers the proton and the neutron. So that's just the idea of it. Something always goes round. Something always goes round that contributes less. That is the electron. Every atom is always made up of every single thing inside. The bigger cycle is the atom. But inside this atom, we have money that is moving around, people that are in the office. So that's just how it is. Money that is moving around and people that are inside the office. So the people that are inside the office are proton and neutron. Why the money that is moving around the electron? So because the money is moving around, if you want to say who are the main people in the office, that is the thing that are responsible for the weight of the office. It is just the proton and neutron. That's atomic mass. That's what I was trying to explain earlier. So I don't know if anybody has any question before I move to the next slide, because I think I've already done justice to this one before now. Can anybody?
Continue, sir. Continue, sir.
Continue, sir.
Okay. So now, we talked about this atom now. So now, before now, there were different ways that people describe them, this atom. But some of these ways they did not make sense. They did not make sense. Before, some people said that the atom is scatter, there's no organized structure. This one do like this, that one do like that. But now, the Planck's theory and the Bohr's theory, they proved that the atom, that is the theory that proved that this what they call it, these protons, they don't go anywhere. They stay in the center. They stay in that nucleus. And the same thing with the neutron. It was Planck's theory and the Bohr's theory that actually proved that the protons and the neutrons, they stay in the center of the atom. So think of that thing. Planck's and Bohr's theory, Bohr, B-O-H-R-R, sorry, not double R, B-O-H-R, Bohr's theory and Planck's theory, P-L-A-N-C-K-S. Planck's theory, Bohr's theory, they know that prove that these are waiter. They don't go anywhere. And they know that prove that these atoms, these electrons, they move continuously in a particular pattern. So, sorry, I don't know. So this particular theory, the combination of Planck's theory and Bohr's theory, is what brought about the modern wave theory. And this modern wave theory says that electrons move so fast, and they like both and both waves. So you might see something, you might say, there's a theory that I don't know whether this will come out, but just put in your mind somewhere that the theory that tries to talk about particles, or there's a theory that tries to say that atoms behave as both waves and both particles. That atoms behave as both waves and both. So what is the people that will write the advanced physics or advanced chemistry? They know that we need to know much details about this wave theory and what they call it, and the particulate of matter. You would see it in physics, but you don't really go deeper into it. But the wave theory, your advanced level of this thing. But the main thing is just know that the wave theory is one that tries to tell, the modern wave theory is what tries to tell, what they call it, tell you that particles behave both.
Barry. Let me get on.
So someone's mic. As I'm saying, the theory that tries to explain this is what they call the modern wave theory. So now, there are now some principles that govern how these electrons move around. The atom. So the theories are the Hofbauer's principle, the Pauli's exclusion principle, and the Horn's rule. I'll explain each of them one after the other. Can anybody hear me?
Yes.
Yes, sir. I can hear you.
Hello, sir. Please,
You said what?
Please, I was trying to get it. Can you come again?
Okay. I was saying that there's a theory that was used to prove that this thing, the nucleus, is comprising of both the protons and the neutrons. And that theory that are Bohr's theory and the Planck theory. So those two theories came together to prove that atoms they have a nucleus, and in that nucleus, the protons and neutrons stay there steady. So now, the movement of electron now in an atom, there are some principles that govern the movement of electron. And these principles are the Hubble principles, the Pauli exclusion principle, and the Horn's rule. So this is something that I think at some point, these three principles they were confusing to me because I was like, these things and they don't even make any sense to me then. They were very, very confusing. So now we're using this as the same idea to try to understand it very well. So the first principle is trying to say that normally, if you are what they call it, if you go to a high level reference, they always tell you bring it to the VIP station. You must first make them, or go to church. Let me use a church. I think it's better. You go to a standard, or not standard church, a big church that has overflow. They said first, before you start seeing people, before people see people from one place to another place, take them from the main auditorium. You have to first fill up the main auditorium first before you start taking people to the overflow. Fill the main auditorium first before the overflow. So now, in this case of elements, now they are only that they call the places of low energy level the auditorium, while the place of high energy level they call it the overflow. Low energy level the auditorium, high energy level the overflow. So you first fill the low energy level area. You start going. I said according to Hubble principle, the simple way to understand Hubble principle is that you try to use a big term. AUFBA.
My network is failing me.
Hubble principle, AUFBA. Hubble, that is AUFBA. Hubble principle. So according to the principle now,
please come again, sir.
Hubble's principle, I'm coming again now. Hubble's principle, AUFBAU. Hubble's principle.
Please come again. A was
AUFBAU.
Okay.
So that
what are the principles saying?
So according to this principle is trying to say, is trying to treat everybody like as though they are in all these big churches, where if you are in that church, they will first put people in the main auditorium first. Then only when the main auditorium is filled up, you cannot take people to the overflow. Now, in chemistry view, this main auditorium, the main auditorium is similar to low energy level. For the main auditorium in element in chemistry, that main auditorium they call it low energy level, while the overflow is high energy level.
So you said something about high energy level and low energy level. Please come again.
Yeah, I'm repeating it. I said the auditorium, the main auditorium is just write in your note somehow. Main auditorium.
I can't hear you.
Low energy level. Can you hear me now? Can you hear me now?
I can hear you now, sir.
Hello, yes. Can you hear me?
According to
yes, sir.
So according to the principle, I'm saying just write in your own note now, in some way you write it, right? Auditorium, I'm using a church now as what I'm using as a simple example. A church, the auditorium, main auditorium, just write main auditorium equals to low energy level. Right? Main auditorium equals to low energy level. Then write overflow equals to high energy level.
Main auditorium equals to low energy level.
Then overflow equals to high. Overflow, that is the overflow.
Okay.
Is equals to high energy level.
Okay.
Is equals to high energy level. So now, if you went to church now, would they feel the high energy level first or the low energy level first? If you went to a big church, would they feel the high energy level first or the low energy level? So that's what our boy is trying to tell you. They'll first feel the low energy level, and I don't know why they said it like that, but I'm just using the example of the church. They tell the auditorium to be the low energy level, while overflow is high energy level. So low energy level will first get filled up before you take people to the high energy level. If it's a restaurant, though, it's not really true, but say in a restaurant, they will first allow the masses to fill the main place. Then VIP is only when the main crowd has filled up. They will not tell you, okay, if you want to enter VIP, enter VIP, come and enter. You pay extra money. So that's how it is. That's the same way it is. They will first need to fill the lower place before you go to the high place. But in chemistry term, according to Obvo's principle, just say that when according to Obvo's principle now, if I'm trying to bring Obvo's principle now to the grammatical chemistry term, they would say it like this.
Okay.
When filling an orbital or an element orbital, you always fill the orbitals with the low energy level first before filling one with higher energy level next. That's just the Obvo's principle. When you are filling orbitals in an element, you fill the ones with low energy level first before filling one of high energy level next. That's Obvo's principle. So if you can remember this particular scenario and link it to Obvo's principle, you should be able to remember the principle.
Sir, please come again,
So
like
now,
define it chemically, like define it in chemistry terms.
okay, when you try to fill an electron's orbital, you first fill the low energy level
When you
before
try
trying
to,
to fill up an electron's orbital.
okay.
You must first fill the low energy level before you must first fill the orbitals with low energy before you start filling orbitals with higher energy. That's the low energy level you first fill up before higher energy level. So now I think I'll soon be ending this lesson now once I explain the remaining two principles. Now the next principle we are going to be going into is the Pauli's exclusion principle.
Hello?
The Pauli's
Say it
exclusion
again.
principle.
What?
Pauli's
It's
exclusion
what?
principle. PU.
It's what?
Pauli exclusion principle.
Exclusion.
Pauli exclusion principle.
poly,
So now,
like Paul.
yeah, Paul, like Paul, Paul, Paul. Then put A at the end, Pauli. That's Pauli.
Okay.
Pauli
Only
exclusion principle.
exclusion.
Principle. So now, based on this principle, what he's trying to say, I'll still use the same church analogy. According to him, this Pauli is like as if he's the chief usher. He's not saying every single place, every single spot, don't put more than 2 usher in this junction. Don't put more than 2 usher in any junction. So now, what does this mean in chemistry term now? For every orbital now, every orbital can only contain 2 water. Yeah, you can fit only 2 electrons at the same time. In the same orbital, you cannot take more than 2 electrons in a particular orbital. You cannot take more than 2 electrons in a particular orbital. But now, this particular chief usher now is a very, very, very strict one. He say the 2 usher that you now, they must be 1 male and 1 female. 1 male and 1 female. So now in chemistry term now, it is now saying that these 2 electrons that you put in that single orbital must have opposite spin. So one of the electron must be opposite spin. So if one so I see like If one is moving up to down, up to down, up to down, the other one must be moving side to left, side to right, side like left to right, left to right. They must not have the same spin direction. That was this police exclusion principle saying. He said two things. He said in a particular row in the church, don't put more than 2 ushers. And those 2 ushers must not be male. They must not be male or female. They must be a male and a female. In chemistry term now, when we now brought it to chemistry term, it is now saying that in every orbital, you must not put more than 2 electrons. And these 2 electrons must have different spin. Not different charge, different spin, like to spin something around, to rotate something, like spin. They must have different spins. So that's the 2 things that this Pauli exclusion principle says. So if they ask you to define, to state the Pauli's exclusion principle, the principle states that at any given orbital, there cannot be more than 2 electrons. Can anybody hear me?
Yes.
No.
Yeah, so at any given orbital, there cannot be more than 2 electrons. And these 2 electrons must have opposite spin. That's the simple definition of the Pauli's exclusion principle.
Must have 2 opposite ones.
Spin.
Okay.
So now let's move to the last one for this evening. The next one is so the next one is the Hund's rule. Hund's rule. Hunds. Hund's rule.
H what?
Hunds. Hunds.
Hunds. Okay.
Hund's rule. So now this Hund's rule now is now trying to is how he's trying to say is that he's trying to now say is now that everybody trying to talk to the usher saying that as you are sharing food now, give everybody one first. Only when giving everybody one, the food remain before you start giving them two. You get that's what he's saying. He's saying to every single person in this particular auditorium, give everybody one plate of food. They are doing party. Give everybody one plate of food first before you start telling them take extra. Everybody must first have one. So this Hans rule is a very good guy. It was him that was always in every party, everywhere for the good. But it's not him that is in every party. But maybe people can learn from that. Before you give any now in chemistry term now, it is orbitals I'm not talking about. Before you fill any orbital with 2 electrons, we know that they already said I am this guy that. What's the name of this guy? Osborne said that I'm sorry, Paulie said that they must contain to every orbital. Paulie said that every orbital must contain 2. So now this horn is not saying, okay, yes. So 2, I mean no, but wait, before you give anybody 2, or before you give anybody food, before you are sharing 2, see what you do. Give them one first. It's only when everybody has collected one, you can now start sharing 2. You said what?
Sorry, please come again.
Okay.
Is
Can you hear me now?
Hundreds or hundreds?
I can hear you.
It's Hund's rule. Hunds. Hunds.
Is it
Rule.
hundreds?
It's Hund's rule. Hunds.
Okay.
So now what I said that this rule says that before you start sharing food for everybody, as you're sharing for everybody, give everybody one first. Let everybody hold one first before you start giving everybody extra. May everybody first collect. Don't give one person 2 at the same time. That's the critical thing about this rule. Don't give one person 2 at the same time. You must first give everybody one. When everybody has collected one, and you're sure that everybody has collected one, you can now start sharing the next one for everybody. Make everybody first before you share extra. Don't give one person 2 plates. So now in chemistry term, that's saying every orbital in an electron with orbital always share electron 1. Always share electron one by one first. Then when every orbital receive one electron, you can then start pairing them up. So now in chemical definition, you say before in an element, in an electronic orbital, every orbital are first filled up singly first before they are then paired
In an
up.
what?
In an electronic orbital,
Okay, sir.
every orbital in that energy level are always filled up singly first. That's one single, like singular and plural. They are always filled up singly first before they are being
Every
paired up.
orbital in that energy level.
They are filled up singly first.
Must be seen first. Singly first.
Yeah,
Before
filled up
pairing them
singly
up.
first before pairing them up. Before pairing them up.
Please, sir, come again, please.
Okay, so in this we say that in an electronic orbital, every orbital are filled in singly first, singular and plural, one by one first. You fill them one by one first before you give them two, before you pair them up. So now, if you can use this, if you can put this in your mind, okay, you came to church first, and they said the first principle is the off-boss principle. And according to off-boss principle, he said that before you carry anybody to the overflow, first fill the main auditorium. And he said that overflow is high energy level, while the auditorium is low energy level. So now, in seeing chemical now, before you fill up orbitals of higher energy level, you first fill up the orbitals of lower energy level before you start taking to higher energy level. So then now, after you have thought about that one, I say, okay, in the same church now, putting usher now, putting people, or even you can even say you don't use usher. You can say you use seat. You can use seat now. Say on every seat, put people one by one person per seat. No, that will not make sense. Let me know your analogy. Let me use what I used before. Usher, every row in the church, every row, put one or put two usher. It must not be more than two usher. Every single row must have two usher. So now, every of that row must contain one male, one female. It must not be two male, must not be two female. That's based on the Pauli's exclusion principle. Every single orbital must contain not more than two electrons. And these two electrons must have completely opposite spin. So that's what the Pauli's exclusion principle states. Two things in one. Two, and not more than, not the same spin. Must we not have the same spin. So then the Horn's rule then was not trying to explain that, okay, now as they're now sharing food now in that same church now, give everybody one first. When everybody has collected one, share the remaining one to everybody second, like two. So in chemical terms now, every orbital in this energy level must be first filled one first before you start pairing them up to make that two. So that's going to be all for today's class. I don't know if anybody has anything to say. Yeah, I can hear you.
There's a place I missed to.
Okay, I'm listening.
I don't know if you can talk more on this atomic mass again, please.
Okay, I said that atomic mass of I already talked about this atomic mass before, but that's why I did not really spend much time. I said we already knew. Yeah, you said what?
The theory.
Atomic mass. That theory. Okay. Yeah, I talked about the theory, and I said that there are two theories that made the atomic theory, that made us have the view of atomic structure as we have it now. You know, I said the nucleus. In the nucleus, we always have protons and neutrons in the nucleus, and we have electrons moving up and down. So the people that propounded that theory, that made people accept that particular thing, their names are Planck and Bohr. So the Planck's theory and the Bohr's theory are the one that prove that this thing is true. They are true. In the nucleus, proton and neutron are there, and they don't usually leave that place. So it was these theories that proved that that was true. So that was what I was trying to talk about. And then I said that electrons now, they are always localized at the nucleus. They are always at the center of the atom. They are always in the nucleus. So I don't know if we are good to go now.
Okay.
So does anybody have any other question for me?
Thank you, sir.
Thank you, sir.
Okay. Okay, you're welcome. So now that will be the end of today's lesson. So the next time we'll be having chemistry, you would see the information on the next group and we'll continue from here. But I don't know, that class might be a question and an answer class where you would be bringing your question. There are videos. First of all, before we leave, there are videos that we've been posting on, there's a link that they always share on the group on videos. So for you to be able to have the understanding here, so you will not be caught off guard, go to those videos and watch them. They are on YouTube. The reason why I put them on YouTube is because not everybody has the ability to download the video down. Some people don't have storage on their phone, so you put it on YouTube so that okay, you can watch it there with the smaller data. Watch it, and you just come back. Yeah, so some people's phone has storage issues, so we cannot just put it in one place. So we have to put it on YouTube so that you can access it anytime. You can even do on MCN if you are using data. YouTube data, I think YouTube data is 120 naira. An hour of, I think for a particular hour of this thing of YouTube use, you will use it very well. So just do that and help yourself. The subjects you have, those topics were taught one after the other. So if you have any question from those things, or maybe you got confused, just carry them to the class. By next week, we'll be having chemistry. We'll be having question and answer.
Okay.
I think we'll be closer to your exam. Trying to see how we can help you guys. There's not much time, but the way we can help is what we are trying to do now.
Exactly.
The way we can help through question and answers or through whatever. There would also be a session. Take note again. There will be a session where we would invite some experts that would come and tell you guys about how the PEP works. These people are people that they pass very well. These people, they are people that they did Japan, they pass very well. One of them is going to be studying medicine. Another one was, I think, her phone in UPEP, same point. So she'll be interacting with you guys and telling you guys the pros and cons on how to use UPEP. They are not in lower level, they've gone higher, they are in higher levels, but now they already have the experience. And we're bringing them so that they will guide you through some of the tips on how, even after JUPEP, how you would handle yourself after them. So thank you all for your time, and I wish you all
Thank you. Thank you
success in
so
your
much,
exam.
sir. Thank you for teaching us. Thank you.
Don't
Thank you
forget
so
to
much,
watch,
sir.
go on YouTube and watch this one so that by next class,
They don't scatter my body.
the next class will be explaining,
And they call
we'll
me
be
can go
solving
very
and
full.
preparing them. So thank you all and good
I
night.
been get
sir.
class,
Good night,
so
sir.
Good
we
night,
just
sir.
finish now.
Thank
God
you.
bless you, sir.
Yeah, thanks, Janet.
What is
God bless.
calculation? What is calculation? What is calculation before? Okay.
Okay, so thank you. No, I have.
Yeah, I understand.